All right, and so now for the same exact example right here, we have now arrived at part B of the example. So let's spend some time reading the wording description of this part B of our example. So if we are actually trying to compare words by words from part A right here, then it's exactly the same wording, except for here we're looking at a sample of 50 college students. So now entirely as the way how the words described here, in a sample of 50 college students, we want to find the probability that less than 20 of those 50 college students is in business major. So the question remains exactly the same. It's just we change to a different sample size. That here does indeed cause some impact right here for us. So now I just want to point out that it's a completely brand new problem right here, even though it's the same idea. So now back on my board, I have all my right to retain that information, all of that information regarding the beginning population. We still have that same population proportion here being 30%. And so now we're going to draw samples out of this beginning population. So this time, and starting in this part B, now I can start putting the steps in the formal structure over here. I can start putting up the formal structure of the steps, how the steps are being carried out in a certain order. So first we know that our samples that we use in each of the samples here is 50. So in each of the samples we have 50 college students. And so again, as a scratch work reminder over here, the whole idea here means in some sample of 50 college students, we may be as unlucky as having none of them being in a business major. Some other sample we may find as lucky as 14 of them being in the business major, but these now are all out of 50. And then there may be some sample that shows 15 business major students out of 50, and then so on and so on. And then some sample may be as lucky as 40 out of 40. So these are all, this is a p hat, and these are all p hat values. So in the end, what we have here now is a random variable capital P hat, 50 this time, which represents the proportion, generally, the proportion of business major, because we're still studying the exact same category here. So now capital P hat 50 represent the proportion of business major in a sample of 50 students, and of course college students. And so now we further realize that we're not only having one value. What we have here, this random variable here, represents an entire population of sample proportion values right here. And what we have here may be one of these values here. And so in that way, looking back at the wording of the problem, we want to find the probability that less than 20 of them is in business major. Find the probability, or what is the probability that. So formulating the problem, symbolically we can write find the probability, P in parentheses. We want any of our sample to come out, and of course a sample out of size 50 right here. So we want any of our sample to come out with less than 20. But now to be precise, this is the count. So we want our count of business major in any of our samples here to be less than 20, but 20 out of 50. All right, and so now in decimal, 20 out of 50 is the same as finding the probability where we want our p hat 50 being less than 0.4. So if we're looking back at part A a little bit here, then it may or may not be the same number here, but the point now, what I'm seeing here, the point now is that we are looking for this kind of problem here. It has the same generality with the problem we have done in part A earlier. We want to find the probability where the sample that we picked up in this requirement, having 50 people inside right here, we want to find the chance that our sample falls into an interval of values. This is an interval of values. We want our p hat 50, this random variable, to fall below 0.4. All right, so now formally as the next step, now we realize that this is a population of sample proportion values. So the center, where symbolically I regard to that as a mu p hat, the center is found as easily as 0.3, because this result is stated in a theorem that I mentioned earlier in part A. But according to that result, then it's just simply equal to the population proportion from the beginning population. Sigma p hat, which means the average spread of this population now, is going to be calculated through an easy formula. Square root of 0.3 times 1 minus 0.3. Now, unlike what we have done in part A, where sample size was 40, here we are going to divide by 50, being the sample size in each of our sample here. And so this calculation will come out as following. On my calculator screen now, I'm going to have 0.3 times 1 minus 0.3. And I'm going to divide all that by 50. But this quotient here needs to be inside a square root. So I'm going to take the final square root of the entire quotient here. So now I'm going to go square root, and here of the previous answer, and hit enter. So this is now our average spread. So I could have also mentioned this back in part A, but usually throughout all of my lectures, for when it comes to sigma p hats, usually I'll round to 4 decimal places. But make sure you watch for the rounding requirements in every single problem that you are working with. So here it's going to be 0.0648. So this is the average spread of this distribution from where the center is. So now this is formally the step right after we have formulated our question symbolically. So the next step now is to verify whether we can solve the problem here by putting our data as a population data here on a bell curve or not. So in order to do that step, I need to do the following calculation. The sample size 50 that we're using, I am going to multiply with 0.3. This is the given population proportion that was indicated. So this product will come out with a count. So let's find out right here. So 0.3 times 50 comes out with a count being 15. And this count is above 10. And so again, if anyone is curious about where this 10 comes from, for our class here, just take that as a rule. We want to always multiply our sample size with the given population proportion, and to come out with a product or a count above 10. So that tells me that I meet the first requirement. So again, we're currently checking to decide whether we can work with this problem here as a bell curve problem, or we're trying to determine whether we can bring this population data on a bell curve so that we can solve the problem as a bell curve problem. And also we need to do the second requirement check right here. So now I'm going to go 1 minus 0.3, which will eventually be a 0.7. I'm going to multiply with the sample size that we're currently using for the problem. So this is namely the same as 0.7 times 50, which will come out being 35. and this once again also above 10. So the same sample size here, meets both requirements. That the sample size multiplied with the proportion and the sample size multiplied with 1 minus the population proportion. They're both giving us the two counts greater than 10 or at least equal 10. So now, having passed both requirements here that guarantees our sampling distribution of the proportion here can be placed on a bell curve. Now we're ready to roll into the next step. And so I just want to give another remark here in case I didn't give it out in the earlier at the end of part A right here. But the whole reason of checking for whether we can use the bell curve to solve the problem is that be aware that there are other problems out there where the sample size does not meet, or it may fail one of the requirements here to put our data on a bell curve. So this is the reason why this step is now legally need to be placed before we draw our bell curve data. And there will be other problems where it's exactly the same kind of problem, but we can fail having a sample size that meets the requirements. But those kind of problems here, we'll wait for another lecture right there. We'll wait for a different lesson. So now that we know that our sample size here guarantees that this sampling distribution can be placed on a bell curve, now we can imagine all sample proportions can be placed on a bell curve. Left are all the low values, right to the right hand side are all the high values. Center is right in the middle at 0.3 as a value. And so these are all the capital P hats, 50 this time. And so now 0.4 now can be placed on the bell curve. And this bell curve is further known to have an average spread being 0.0648. And so with 0.4 being clearly to the right hand side of the bell curve center, this question now has a picture as following, as a shaded area completely to the left hand side of 0.4. So 0.4 is a value that we want, that we're looking for in this problem right here. We want the count in each sample to be less than 20. So 20 out of 50 is the same as a 0.4. So that's the number that we want to look for in this problem right here. But then translating that into a picture, then that's the shaded area shaded to the left hand side of 0.4 on this bell curve that is now legally accepted. And so now the z-score step will be the next step right here. From where our value that we're looking at, I'm going to subtract 0.3, the center of the bell curve, and we're dividing that by 0.0648. And that is the z-score for this value 0.4. So now on the calculator, 0.4 minus 0.3, and divide that by 0.0648. This is the z-score for 0.4 on this current bell curve that we're looking at. And then again, I am going to round this value. It's just my choice throughout all of the lectures about z-score over here. I use 2 decimal places z-score. But make sure when you're doing your own actual problem, then watch for rounding requirements here. So here I'm going to conclude a 1.54 on my writing board. So the z-score is 1.54. So that means this area symbolically as the probability problem where we want p hats 50 to fall below 0.4. This probability or this area is the same as the probability or the area on the z curve or the standard normal distribution curve where z-score falls below 1.54. And so now upon realizing the connection between the answer to our work and the answer that will come out from the standard normal distribution. At this point, we are ready to use the normal CDF command right here. So what matters now is to run our normal CDF command. On my calculator, again, and on any calculator, to retrieve the normal CDF command, we will go second distribution and roll down to the option that says a normal CDF. On this advanced version of the calculator I'm using, then it gives us a manual. And TI-83 or some older TI-84, instead of giving manual as you saw earlier, will give you a direct command as like this with an opening parentheses. So now back on the version of the TI calculator that I'm using. The area is shaded completely to the left hand side, so I'm using -1 E99 here. To have access to that E right here, -1, and then second comma, and then that will bring up E and 99. That's the lower end of our interval. The upper end is the z-score that we have calculated on the writing board earlier, 1.54. So 1.54. And then in my style of how I teach my stat students, I always want my students to use the normal CDF command, default mu and sigma to 0 and 1 as following, as indicated here. 0 for mu and sigma equals 1. This is the standard for the standard normal distribution curve. And so now I'm going to hit enter and get ready for calculating the final answer. So the older calculator will run the same command like this, where you will have to type in these values here separated by commas. And so now it's just a matter of hitting a final enter to come out to the final value right here. So 0.9382 is that probability. So I'm going to use 4 decimal places, but to complete the syntax here, to complete the command here, -1 E99, comma, upper end 1.54, comma 0 for mu, comma 1 for sigma, close the parentheses. So this is assuming that anyone viewing the lesson here is using the TI-83 or 84 calculator. But in case you use a different calculator, there should be, but you must be learning that on your own right here. But there should be command or syntaxes there that serve the similar functionality. So now the final answer came out, and as I said earlier, I'm going to go with 4 decimal places. So 0.9382. And do watch out for rounding requirements in each of every little problem that you're working with out there. Or to make it easier, you can put this as a percentage. So this probability is reflecting about 93.82% chance. All right, and so now briefly as the meaning of this final answer again, or as an interpretation of this final answer. Anytime, provided that we already knew the population proportion for this category being in business major among the college students, then anytime we picked up a sample, anytime that we have picked up a sample of 50 college students, then the chance of finding less than 20 of the students being in business major, which is the same as the chance that we are having our p-hat 50 being less than 0.4, that chance there is a 93.82% chance. Or we're looking at about 93.82% of time that we're going to find sample where less than 20 of them being in business major, less than 20 of them in a sample of 50.